now we're going to take this stuff that we're learning about sound, and we're going to actually apply it to some musical instruments. If you recall, and this is just a visual to get you to remember, we talked about standing waves. We did demonstrations on the ground here. I had a standing wave demonstration here with, I believe, a yellow string. And this is just a visual to remind you of the standing waves. And what we're going to talk about today is standing waves on a string for a musical instrument. It could be a violin, a cello, a guitar, doesn't matter. We're going to set up standing waves on a string. We're going to talk about what frequency we're going to get from that musical instrument. That's what we're going to figure out right here. Okay. So this is going to be the distance, the length of the string. The first we're going to set up is a standing wave that looks like this. For this particular standing wave, how many nodes are there, Hannah? Two nodes. How many antinodes, Hannah? One. Two nodes on the ends, and one antinode in the middle. Okay. How many wavelengths then equal L? How many wavelengths equal L, the length of the string, if this is the way we're setting up our standing wave? Emily X. Half, right? So if you look at it, in order to get one full wavelength, we have to start here, but we have to continue and end all the way over here. So the wavelength is going to go, the wavelength of the wave is going to go from there to there, standing wave. So we have half a wavelength is equal to L. In other words, a wavelength is equal to 2 times the length of the string. Well, I said we need to get to frequency. So remind me again, Wicket, how are frequency and wavelength related? The velocity equals the frequency times the wavelength. So if we're trying to figure out the frequency of this, it's going to be equal to the velocity divided by the wavelength, or the velocity divided by 2L. Now, this velocity is the speed of the wave in the medium. So the wave travels back and forth in this string at a certain velocity, and that would be the velocity in this particular equation. We're going to do 2 more. We're going to do one where it looks like this. Oops. That way, where we have 3 nodes and 2 antinodes. It looks like this. In this particular case, how many wavelengths equals the length of the string? Christine?
4.
It's actually not a 4. How many wavelengths equals L in this particular case? Miss Song? 1, because it turns out that the wavelength is just for one wave, would look like that. So it's just one wavelength is equal to the length. So if we're trying to get to the frequency, then the frequency is equal to the velocity divided by the wavelength. Well, that's just the velocity divided by the length. Okay? One more. Let's say we have 4 nodes and 3 antinodes. How many wavelengths equals the length of the string? Now, Dana? 1.5, right? Because one wavelength would be from here to here. And then this would be a half of a wavelength. So yes, 3 wavelengths over 2, or 1.5 wavelengths equals the length. So then we know the length equals the wavelength equals 2L over 3, which means the frequency is going to be equal to the velocity divided by the wavelength, or the velocity divided by 2L divided by 3, or the frequency in this particular case is going to be equal to 3 times the velocity over 2L. And believe it or not, we're actually setting up a pattern here. It might not be obvious at this particular point, but let me change things slightly. Would you agree that V over 2L is equal to 1 times V over 2L? Yes? And V over L is equal to 2 times V over 2L. And then the third one is 3V over 2L. Pattern. the frequency for a stringed instrument is equal to n times v over 2l, where n is called the harmonic number. N equals 1 is called the fundamental frequency. It is also called the first harmonic. N equals 2. Who wants to guess what that one's called? Good for you. It is called the second harmonic. N equals 3, the third harmonic, so on and so forth. And these are the frequencies that you will get out of a stringed instrument.